Hi, so my talk is called Immutability, or Putting the Dream Machine to Work. So I've been a front-end developer for 8 years now. I was at the New York Times for 4. I recently left to join up with a company called Cognitect. They're a consultancy, and they also have a database. And at Cognitect, I think we believe that a lot of software is far too complex. And there's ways to achieve a lot more simplicity in the type of systems that we write. One way to achieve simplicity is through immutability, by embracing immutability. So Cognitect stewards Clojure and ClojureScript. I'm the lead maintainer of ClojureScript. Those languages emphasize immutability. We also have a database product called Datomic, which is a immutable relational database. I'm not actually going to talk about any of those things today, or we'll only talk about them a little bit. The thing that I really want to talk about today is the Dream Machine. So if you have not seen this book or encountered this book, this should be #1 on your reading list if you are involved in interactive computing in any way, shape, or form. This was recommended by Alan Kay as one of the best histories of how interactive computing came to be. It will make you laugh, it will make you cry, and if you have anything with UIs, it will fill you with a sense of wonder. So J.C.R. Licklider was a psychologist who, at the time, realized that there was not a serious enough perspective on the role of human psychology and human factors in computing systems. Also, a lot of people didn't believe interactive computing systems would be of any utility whatsoever. And he really paved the way through ARPA to make sure that research institutions were putting the time and effort into discovering the results of interactive computing. So he is most famous for 2 essays. One of the famous ones is called the Man-Computer Symbiosis. So Licklider basically predicted my talk 54 years ago. I was going through this paper for actually the first time 2 days ago. And he says something very specific, which I'm going to talk about quite a bit today. This talk is a little bit of history, a little bit of data structures, and a little bit of examples. So in this paper, he sort of lays out what are the types of hardware and software things that are going to pave the way for interactive systems. He saw computing as a way to augment the human intellect. So he says in this paper, the Trie memory scheme is inefficient for small memories, but it becomes increasingly efficient in using available storage space as memory size increases. The attractive features of the scheme are these. #1, the retrieval process is extremely simple. Given the argument, enter the standard initial register with the first character, pick up the address of the second, then go to the second register and pick up the address of the third. If 2 arguments have initial characters in common, they use the same storage space for these characters. And I'm going to actually talk about this quite a bit. Here we have several people that benefited from the culture that Licklider created. John McCarthy received considerable funding. He is the inventor of Lisp, artificial intelligence, interpreters, functional programming, garbage collection, all things which are critical for doing anything that you guys are doing today. He was a mathematician. At the time, using computers was extremely difficult. He believed that actually programming the computer itself should be a real-time interactive activity. You can thank him for the interactive console. That's definitely due to John McCarthy. To his right is Ed Fredkin. He was a Caltech dropout at 19, went to the US Air Force, was a fighter pilot, and then when he was very young, was pivotal in hacking these early computers to do impossible things, to build interactive systems. Ed Fredkin also invented the Trie, and that's spelled T-R-I-E, and that's what we're going to talk a bit about. So Alan Kay is another important figure. He also benefited from the culture that Licklider created. Alan Kay well understood John McCarthy's ideas. He built an interactive programming language, but on top of that, he sort of erected the edifice that we are all familiar with today around object-oriented programming, as well as blazing the trail around what we consider modern user interfaces. So here's an image that I think is very inspiring. A big goal of his was that computing should be simpler, that it should be available to people at a very young age. Here are some boys and girls, and they're interacting with a live small-talk programming environment. And they're doing things that, they were very lucky, right? They were experiencing the future of computing when most people were still doing BASIC, right? There's a really great article I recommend reading. This is an article that I found on the Atari archive. It's Marion Goldine, and she was 11 years old, and she was lucky enough to experience a Xerox Alto and Smalltalk, and she describes, when she's like 12 years old, what it was like to program one of these machines. So she directly benefited from the Dream Machine. She's actually has for years been a UI programmer at Apple. And she went off to do this because of her experiences with the Smalltalk environment. Anyways, you can fire up a Smalltalk environment today. There's an open source one called Squeak. It's quite cool. If you open the system browser, which uncovers the entire internals of that system, you will encounter something which is very familiar to JavaScript programmers. Model View Controller. Trygve Reinskog and Adele Goldberg and others at Xerox PARC invented MVC, 35 years ago. Long Shadow. People are still talking about this stuff. I would actually argue we haven't really advanced much beyond it. But that's okay, because at an abstract level, MVC is a sound separation of concerns. We want users to be able to interact with their domain. We want to have intuitive visual representations of that domain. And as programmers, we want to coordinate that abstract domain and those abstract visual representations such that the user has a pleasant experience. But I would argue that implementations leave much to be desired. That's having worked with a variety of MVCs over the years. That's because they're erected on top of stateful objects. You have stateful models, you have stateful controllers, and you have stateful views. And so the crazy idea that I'm going to throw out is I think that Licklider was correct. If you build your user interfaces around trees, really cool things happen. So trees. So this is the data structure part of the talk. I'm just going to reuse some slides because these slides are amazing. They were done by Zach Allen at Hacker School. He's a facilitator there. He put these slides together for Strange Loop, and they're just so good, there's absolutely no reason for me to come up with my own. So regardless of whether you like functional programming or not, it's not very important, but all these ideas apply if you like object-oriented programming. But we need to at least understand how these data structures came to be and why functional programmers like them in order to understand how we might use them if we prefer the object-oriented approach. So functional programmers, they like immutable values. They don't like stateful objects. And when you change something, you just return a new value. As JavaScript programmers, you guys are already well aware of this. You have numbers in JavaScript. They are, thank goodness, immutable. Strings, you're lucky. Not every dynamic programming language had immutable strings. You have immutable strings. So what functional programmers want is that, yes, we know that if we add 1 and 1 and we get 2, that doesn't change the other ones, right? So functional programmers also want this behavior from collections. So if I add a key value to a map, I get a new map, and the old map is not destroyed. So as JavaScript programmers, you're extremely used to destroying data, destroying the past. And we don't have to do that. And I'll demonstrate how this can be done. And so this is where the term persistent comes from. Not persistent in the sense of like you're going to record it to a database, but persistent in the sense that you're not destroying previous values. And they're very fast, and this is actually relatively a recent development. Okazaki talked about purely functional data structures, but that, they're okay and they work. They have good paper complexity bounds. A man named Phil Bagwell, who was EPFL, where Scala was invented, he did initial research in the early 2000s on how you could have really high-performance persistent data structures. And they were further modified by Rich Hickey, and actually it was really Clojure that showed that they could perform well on modern hardware. But that might sound really advanced, but I want to show you that it's not scary. I bet almost everyone here in this room knows what a linked list is. And linked lists have the same properties that we like about trees. So in a linked list, here's a list with 4 things in it, and we store it in a variable x. Well, I can cons some value onto the head of that, and I can store that in a variable y. And now I have 2 values, right? And they share more than 50% of memory. Right? They represent 2 distinct values, but they share more than 50% of memory. I can take the tail of x and cons z onto that. Now I have 3 distinct list values, and they all share more than 50% of their memory. So this is a scalable idea. This idea is called structural sharing. So sharing structure gives us space efficiency, but less obvious is that it actually gives you computational efficiency. So if you use structural sharing, you can do these immutable values, and you can update just a part of it, and it will be efficient. So Phil Bagwell innovated this space again. He came up with this thing called the Trie, hash array map tree. Rich Hickey took that and modified it quite a bit in a very clever way, and he invented something called the Bitmapped vector tree. So I know that everybody here knows what an array is. So a bitmap vector tree is like an array. It's high-performance random access, and you can append to the end quickly as well. So the way that they work is data lives in the leaves. It's a prefix tree. Remember, Licklider was talking about this in 1960. It uses it's a prefix tree to find a particular value, and it's done in a bitwise way. To make that more visual, so in the tree of a persistent vector, you have an array of arrays. So at the root, you have to pick some fixed size, say 4. And then every element of that points to an array, which is also the same size. And then those arrays point to more arrays that are the same size. Finally, you're going to hit a leaf node where you have actual values. Okay, this sounds kind of interesting, but how the hell do you look up anything in this? So imagine we want to get the 106th element. So we can do this really cool trick. That represents a binary number. We can use bit masking to find that thing. So we can bit mask off the first 2 bits. This tells us to look at index 1. We can bit mask the next 2 bits. That takes us to the next level. Look at index 2. Bit mask again. Finally, it says the value you're looking for is at index 2, and that's 106. So if you know anything about modern JavaScript engines, array accesses and bit shifting is about as fast as you can get. This is going to be the engine optimizes this in pretty wild ways, which I'll show that too. But what about update? So this is where the structural sharing comes into play. If I want to update, for example, I want to replace 106 with the string foo, how much work do we have to do? We only have to clone the arrays on the path that changed. All other paths that weren't involved in the change don't need to be updated. So that's how much work we have to do to update that thing, and none of the other nodes are going to change. They all stay the same. So this is where the structural sharing we saw with linked lists happens with trees. So you're probably thinking, well, the 4 seems like a weird number to pick for the length. And of course, after empirical testing, it turns out that 32 is a really good number on modern hardware. You do a bunch of tests, and 32 works out the best in terms of how expensive is it to update versus how quickly we can look something up. Okay, just to give you a sense of how good such a wide branching factor is, 32 to the 7th power, that's 34 billion elements on a 64-bit OS with a 64-bit VM where the values are 64-bit. If you do that in a regular JavaScript array, that's 256 gigabytes of RAM. I don't think anybody in this room has a laptop with that much memory. To update something in this data structure only requires 7 array updates. To access anything, at most you need 7 array accesses and some bit operations. Okay, so that's a lot of talk. Let's see some numbers. So this is a recent build of V8. I've exported all the functionality in ClojureScript via a library called Mori, which is available on NPM, as well as for the browser if you want to do that. So what I do is I build an array, and I just push 1 million elements to it, and I time that. And then I do this with a persistent vector. And I just calculate the average. Well, it looks like 83 milliseconds on this particular machine. And then we have an average of about 288 for persistent vectors. So it should already be shocking because this is not an order of magnitude slower, right? This is about a little bit more than 3 times slower. That's already cool. There are many applications that could benefit from these data structures that don't need just the craziest amount of perf. I'm going to show something a little bit crazier. So we've been doing persistent data structures for 7 years now in Clojure and ClojureScript. So we've gotten more and more clever about what optimizations you can do. So you guys might be familiar with object freeze. So of course, all of our data structures are already effectively frozen, but we have a corresponding operation called it's called transient, but we imagine it's like object.thaw. And we can get in 01 time a mutable version of the persistent thing, and we can also make it persistent again in 01 time. So how does a transient vector compare to a mutable array? it's faster to build a persistent vector than it is to mutate a mutable array. So that's pretty crazy. To show that this is true on engines other, or not faster, but the performance is about the same, or not so bad for other JavaScript engines, this is a recent build of JavaScript core. It's not significantly slower, right? So we have all these magical properties that arrays don't have, and we can achieve the performance of mutable arrays. Okay. So that's awesome. So this is because so many people have been building the dream machine for us, right? Just so much research has gone into optimizing dynamic programming languages, and I got really excited because recently WebKit sort of kicked up the notch again. I felt like things were stagnating a bit with their FTL JIT, which is a 4th tier, and that tier is going to absolutely love the type of code that's involved in doing these kinds of data structures. So there's more excitement to come. Nick Bray talked on Thursday about opening up the door to shared memory parallelism. So ClojureScript is already ready for that. ClojureScript data structures are already lock-free. So you can do parallel operations on them without locks. OK, so hopefully you're excited about trees and you're convinced that maybe Licklider had a good idea in 1960. So I want to see, well, what does this mean for interactive programs? So I built a library 5 months ago called Ohm. Maybe some of you have heard of it. It basically marries the suite of tree-based data structures with React. And it turns out that these are a really good pair. And let's talk really briefly why. So we can now represent our application state as one giant immutable value. And then React says, oh, well, you can apply a function to that, and we're going to compute some virtual DOM, which is another value. And now if I update my immutable app state and I get a new value, I can apply that function again, and React will produce some new virtual DOM. And the way that React works is it applies a very clever diffing algorithm on these two virtual DOMs, and then that creates a minimal change set. But what's fascinating about this is that what happens if we flip v1 and v0? For free, React will give us the reverse change set, right, for free. So this means that we can do undo, redo trivially. You can jump to an arbitrary point in time. You can also do things. It makes actually computing deltas faster. It makes that, which makes synchronization simpler. For example, if you want to roll back your app state on an error, you can just jump back to the previous application state, the snapshot. You don't have to manually reconstruct what your app looked like before the error occurred. Lots of cool stuff. It's not just about undo and redo, which some people get confused about. Okay, so it's most fun to show an example that I did not write. So I said. I did a version of to-do MVC with Ohm, and I said, I think I can do undo pretty simply. And I was able to do it non-invasively. I did not change any of my to-do MVC code. I did in an external change, and it was 5 lines of code to add undo over the entire state of the to-do MVC application. So this guy at Ableton, this guy Jack Schradler, said, well, maybe David Nolen's pulling my chain here. Does this actually really work for a less trivial thing than to-do MVC? So he decided to build a 64 by 64 pixel editor. The pixel surface, the frame, is represented as an immutable vector, and that's 4,096 values in there that represent pixels. So let's see this guy in action. So I can select a color here, and then I can, start drawing some things. Let's resize that. On the right, you should see the history accumulating. I can go over here, and I can click undo. I can click redo. I can scrub, and you see the preview on the left. Oops, I didn't mean to do that. And I can do this forever. I've done it. I've done like 200 levels of undo, and the app is still responsive, good memory usage. It doesn't slow down. So that's pretty cool. So how complicated was it for him to actually implement that functionality? This is the entire code for undo, redo, the preview, as well as exporting it as an animated GIF. These are very simple functions. It's about 60 lines of code. This is a nightmare to do in a mutable system. If you've ever tried that before, it's not fun. And how much memory does it use? So if you took an array and you cloned it 100 times because you wanted to preserve the state of your frames, and you updated 1 pixel, it takes about 1.7 megabytes to do this. If you do the same thing with a persistent vector, and you snapshot it 100 times and you randomly update a pixel each time, it takes 0.2 of a megabyte. It's almost an order of magnitude memory savings to use persistent data structures for this. Okay, so we're nearing towards the end. So I use Clojure and I use ClojureScript, but I also do a lot of JavaScript. But I understand that a lot of people don't want to do ClojureScript. Lisp is still too crazy for a lot of people. So I spent some time about 2 years ago exporting all of ClojureScript's data structures, as well as the entire standard library for interacting with them, in a library called Mori. If you want to experiment with like, what type of user interfaces can we build, given the availability of really fast, really expressive, persistent data structures. I highly recommend checking it out. I've tried, for the most part, to follow conventions that exist in Lodash and underscore or what have you. But it does a lot more. I mean, there are a lot of data structures. We have sets, hash maps, sorted sets, sorted maps, the persistent vectors I talked about, and some other things as well. And I actually, there's a lot of cool possibilities here around Sweet.js and Mori. People have done some experiments where by using Sweet.js macros, you can, instead of having arrays becoming arrays, you can create persistent vectors, and if you have a little object literal syntax, instead it will produce a persistent hash map. So that's it. Hopefully that didn't take too much time. Cool, thanks.